Hello and welcome. My name is Trish Buxton, Chair of the Hydrographic Society UK. I would like to provide a short introduction to the Society and this webcast. The Society provides a forum for all those involved in activities related to hydrography and associated disciplines, both in the UK and overseas. The Hydrographic Society UK encompasses a wide range of specialisms and activities. One of these activities includes the Remote Hydrography Conference, which was planned for this month. This two-day conference and small exhibition will focus on the latest innovations, applications, and deployments in remote and automated hydrography. We were all looking forward to meeting at our conference, but sadly, due to the ongoing coronavirus, we recently made the decision to move the event to next year. As the topic of remote hydrography is extremely relevant and important, we wanted to bring you this webcast in order to highlight a variety of related topics, as well as provide an insight to the presentations we will have during our conference. I would like to give special thanks to all our speakers and of course to our sponsors for remote hydrography, L3 Harris, Norbit UK, Mariko Marine and Unmanned Survey Solutions. This webcast is a series of short presentations from some of our conference speakers and we hope you enjoy. At the end, our Chief Executive, David Parker, will say a few words. From me, for now, thank you all for joining, and I will now hand over to Rear Admiral Sparks.
Hello everyone. For those who don't know me, my name is Rear Admiral Peter Sparks, and I am the National Hydrographer and the recently appointed Acting Chief Executive of the UK Hydrographic Office. It's a privilege to have been invited to give this year's keynote address to the UK Hydrographic Society's Prelude event. I recognise that this is a necessary alternative to an in-person speech, but I very much hope to meet with you face to face in May next year. The subject of this Hydrographic Society event and the future conference is remote hydrography, a fascinating subject, and it is a timely opportunity for us to do so, noting that it resonates strongly with the theme of this year's IHO's World Hydrography Day, enabling autonomous technologies. For some, the concept posits the complete removal of the hydrographer from the primary data collection in the field, and the measurement of the physical properties of our oceans and the seabed through remote means, whether that be uncrewed platforms or a range of remote sense techniques. Like many of you, I perceive that the technologies and techniques that we will discuss will, for the foreseeable future, be complementary and additive to the processes that we've used for many years. We will undoubtedly improve the persistence, accessibility, efficacy, and potentially the accuracy of what we do, but we are unlikely to see the human removed from the process completely. If anything, I sense there will be an increased appetite to better understand our oceans and the blue economy benefits that would be derived from them in the years ahead. The future is bright, the future is blue, which is pretty difficult to say, especially as a Liverpool fan. As an island nation, the United Kingdom continues to rely heavily on the sea for our economic and national security. Understanding this environment will remain key to the future of UK prosperity. Noting in particular that 95% of our imports and exports by volume move by sea. 99% of all internet traffic internationally is transmitted by subsea cables. And the maritime sector is forecast to be worth £1.95 trillion to the UK economy by 2030. These are grand strategic issues, themes and figures. We understand them readily, but not everyone else does. We must therefore be advocates for the UK maritime sector, using the various national and international initiatives and fora that we are involved in to both increase our knowledge of the maritime environment and to promote it more widely. The prevailing and forecast economic environment, and in particular the downturn in hydrocarbon exploration, will require us to exploit ever more efficient and cheaper means of furthering our collective understanding and increasing our productivity. For me, remote hydrography capability is a force multiplier. I paraphrase the old Carlsberg advert in that it affords us the ability to reach parts that other techniques can't reach. I'm currently leading a Royal Navy project to determine our future military data gathering capabilities. We will seek to leverage the lessons learned by industry, who clearly lead in this field, and seek to employ a range of approaches, including satellite-derived bathymetry, SDB, LiDAR, and autonomous vehicles, to enable us to operate over the horizon, overtly and discreetly, in benign and contested environments, without the need to put our men and women directly into the operating environments we're seeking to survey and collect in. Away from defence, the UK Hydrographic Office is currently the primary charting authority for 71 states, some of which are small island but big ocean states. Under a variety of HMG initiatives and programmes, our Hydrographic Programmes team has conducted data collection programmes, improved training and education, and supplied survey capability to enable those countries to better understand their blue economies. However, the size of the task is huge. Many of these states have not had the organic capability or capacity to support meaningful data collection activities in decades. Together, we have faced an uphill struggle to ensure their respective marine data needs in support of SOLAS and efficient navigation, as well as the understanding and protection of their individual marine environments, are met. Again, I expect a range of traditional and non-traditional techniques and approaches will be needed to solve these problems going forward. Capabilities such as satellite-derived bathymetry, SDB, have proven to be notably useful in this regard. The increased volume and fidelity of high-resolution data collection also presents new challenges in terms of the throughput of this information to the end users. I believe we will touch on this today, and I look forward to hearing feedback from David Parker in due course. At UKHO, we continue to develop new and innovative data science capabilities to enable us to explore and develop our analytical and assessment processes so that we may better realise the potential of the worldwide data we obtain and process. I believe strongly that the UK has the technical capability and capacity to remain a leading player in this field and to lead in remote hydrographic techniques that we will see and discuss today. If we do so, it will enable us to better shape and influence the maritime sector and the environmental debate. I wish the Hydrographic Society well in today's endeavour and thank them for their continued work to educate and promote the hydrographic profession. I look forward to meeting some of you in person when the conference takes place next year. Thank you.
Hello, my name is Ross Smith. I am a technical project manager here at TCARTA. We are a hydrospatial remote sensing company based out of Denver, Colorado in the United States. And today I'm happy to present with you innovations in multimodal space-based bathymetry for global littoral mapping. This presentation will center upon Project Trident, which is a National Science Foundation Small Business Innovative Research Grant, currently in year 1 of phase 2 research. This research centers upon the integration of 4 space-based technologies for global littoral mapping. For this presentation, I'll be focusing on 2 of those key technologies, space-based laser bathymetry and multispectral satellite-derived bathymetry. Space-based laser bathymetry is derived from the ISAT-2 ATLO3 geolocated photon data product. ISAT-2 is a space-based laser altimeter originally launched in September of 2018. This laser sensor is a 533 nanometer blue-green laser, which is perfectly well suited for bathymetric mapping, despite the fact it is not originally the intent of the satellite mission. In addition to the sensor capability, the mechanism by which this sensor collects data is also very well suited for bathymetric mapping. In nearshore areas, due to the vegetation mission of ISAT-2, these ground tracks are more closely related than they would be if they were over open ocean, enabling for more dense collection of SPL data over these areas. So in order to extract the space-based bathymetry data from the ATLO3 geolocated photon product, we created our own space-based laser bathymetry extraction tool. This standalone software integrates directly with NSIDC, enabling us to subset and download ATLO3 data directly from the repository and integrate it into our own software. This software takes the transect data, visualizes it for the user, enables them to programmatically extract water surface, refracted bathymetry photons and export them for post-processing to complete a bathymetric profile. We then validated this technology across numerous sites around the world. Today I'll be focusing on one which serves as the exemplar for our results that we found throughout these key areas. So in Saipan in Micronesia, we compared about 30,000 SBL points to multibeam echo sounder and airborne LiDAR data. As you can see here, we got under 50 centimeter root mean square error and under 35 centimeter mean absolute error. This serves to demonstrate the accuracies that we observed across all of our testing locations and really validates the capability of ISAT2 to serve as a remotely sensed in situ data source in lieu of other either older or less sparse or non-existent data sets when conducting such a remotely sensed bathymetric mapping project. The other integration here as a part of Project Trident is integration of ISAT2 data with our multispectral bathymetry toolbox. This is a tool that we developed inside of ArcGIS Pro's software. It works on native Python libraries, enables users to use a log ratio satellite guide bathymetry algorithm in conjunction with ISAT2 data to produce many continuous surfaces at scale as needed. As you can see here, this enables users to interact directly with the scatter plot and constrain their regression based on their observations in a much more extensible fashion than was previously available. As research continues, this will be expanded to include machine learning processes as a replacement to the log ratio algorithm as testing moves forward. So now that we've examined this process and validated its results, we can use it in some commercial processes. So here we have Abu Dhabi Emirate. We were able to extract just under 305,000 space-based bathymetry data points and utilize this to produce 2,619 square kilometers of 2-meter satellite graph bathymetry data. This use case is of note because otherwise we would be left to use UKHO chart points as our only in situ data source. So by leveraging the space-based bathymetry product, we're able to get really accurate, up-to-date, remotely sensed in situ data points without ever putting a boat in the water, while still having increased accuracy and confidence in our data to deliver to our client. The second use case I want to point out is going to be the Lucayan Archipelago SDB project. This is by far our most extensive use of these two technologies and really serves to validate the integration of these moving forward as we pursue automation of this in year 2 of the phase 2 research. As you can see here, we produced over 3.8 million photon depth retrievals from ISAT2 data. We integrated this with 120 individual Sentinel-2 AB multispectral satellite images, resulting in approximately 147,000 square kilometers of continuous satellite guide bathymetry data. This really exemplifies the power of these two technologies when integrated and serves to only motivate us further to expand these technologies. If you have any questions about Project Trident or about these two technologies, please reach out to me at rs@tcarter.com. Thank you very much for your time and have a great day.
Hello, I'm Duncan Mallis, the Chief Strategy Officer for Exocean. Exocean are an ocean data company. We collect data with a fixed price turnkey service using unmanned surface vessels to de-risk our project to the client. We guarantee the quality of that data and the delivery of that data. Using an unmanned surface vessel gives lots of benefits. For not only safety, we don't require a support vessel, so we don't have anybody offshore, which is obviously safer. We use ultra low emissions, less than a car, and for that reason we're a carbon neutral company, and because of all this we offer significant economic savings too. We work for energy major companies, both in oil and gas and renewable industry. We work for government agencies and also to survey companies as well. We operate around the world and take all these locations here, the actual USV piloting and the survey control and data collection part of it has all been done remotely in our operations centres in Greenore in Ireland and Banbury, UK. And currently at the moment in COVID, we're actually doing this from our homes. And to give an example, we recently did a survey in Aruba where we shipped the USV in a 20-foot container, used a local partner to take it out of the container, do a couple of tests, put it in the water, guide it out to the harbour, and then we took over the piloting and the data collection, finished the survey, came back in and reversed the process, and all without having to actually go out to Aruba. We have a fleet of 9 USVs, and this is actually not a Photoshop picture. This is from last week, where we had 2 new USVs which were just being fitted out to go out onto 2 different projects, and 2 existing older USVs which we were retrospectively upgrading with all the latest improvements that we've made to it. And we all happen to be wanting a sea trial at the same time. The USVs can be fitted out with any leading multi-beam sonar, so bottom profiler, side scan sonar, and also sound velocity profilers. The USV connects to a remote cloud desktop, which then we log on to with the USV pilot and the online surveyors, so that we can monitor it all 24 hours a day and in real time. So we have a camera view, so we have 360-degree view around on the cameras. We also have a thermal camera and low light cameras. We have a situation awareness, our cyberdeck, which gives a view of where the USV is and other AIS targets on that USV, and also information as to the status of the USV. And then we have the survey screen, which has all the survey information coming in on it. Just a couple of case studies. We've done over 10,000 hours now of IHO Order 1A work for the MCA as part of their civil hydrography program around the UK, collecting backscatter and water column as well. This is a survey we've been doing a few times now for BP, where we take the USV up to Peterhead. We use a slipway to put it in. The harbour master then pilots it out, or we manually control it and the pilot boat out of the harbour. And then we hand over to the USV pilot, and then we sail 128 nautical miles out to the Macclesfield, interrogate the 4 transponders on the seabed, upload that data, Sonodyne check it. We then come back in and reverse. We've done over 1,000 kilometres of pipeline inspection in the near shore, but also shallow, so they're quite a long way out, but shallow areas, using dual head ultrasonic 2024s. We've also used side scan sub-bottom and also trailing wire CP. And for the offshore wind farms, we've done a lot of foundation, jack up and inter-array cables, and also the export cables, which we then combine with the drone to create a seamless DTM going up out of the water onto the land. It's an example of some of the data we collected in 33 metre seas when all the wind farm support vessels had to go back because it was too rough. And this is a 10 centimetre DTM. And say this is all done remotely. We don't have the support boat out here. We do it all over either a satellite link or a 4G link, or if you're right next to it, you can use Wi-Fi. And this is how we operate around the world. Thank you very much for your time.
Hi, my name's Paul Bell from the National Oceanography Centre in Liverpool. My talk is Remote Mapping of the Intertidal Zone. My co-authors are Clive Neal and Christine Sams from NOC, and Kai Bird, who was at NOC and is now at Marland Maritime. To help you understand what we're doing, this is, on the left, an animation of radar imagery of the tide going in and out, recorded from a radar tower on Hilbury Island in the Dee estuary on the North Wirral coast. And this data is quite old now. It dates back to the mid-2000s. And what you can see in this left-hand animation is the tide going in and out. Sometimes the waterline is very distinct and clear. In other areas, it's much less easy to pinpoint exactly where that waterline is. And that's the point, and that's the difference between this method and older methods. In this case, we are picking an individual pixel and looking at how the intensity or some other image property varies through time as the tide goes in and out. What we're doing is looking for those wetting and drying transitions, and each tidal elevation will, if a pixel in the intertidal zone was at one tidal elevation. If we then change that tidal elevation, the pattern of wetting and drying would be quite different. And so what we end up with is a series of unique pulse patterns for wetting and drying, from which we can match to the image time series and look for the best match between the elevation of that pixel and the changes in wetting and drying that we can see on the imagery. And this is really effective. Here on the left, we've got two images. On the left, we have LiDAR data from 2006, and on the right, this is the estimated intertidal elevation for that part of the D estuary. And the range on this is about 4 kilometers. The tidal range in the D is quite large. It's 10 meters at spring tides. And what we tend to try and do is do this pattern matching over a 2-week window, so we catch a full spring neap cycle. There's a couple of publications listed there at the bottom, and this work was done with a number of partners, Marland Maritime, who now operate this as a commercial service, Centre for Global Eco-Innovation and Liverpool University, who sponsored the PhD of Kai Bird. And later, we had an Innovate UK grant to do the technology transfer to Marland, and it's been the subject of a couple of different industry awards since then. We've also been working on adapting this to work with satellite data. The beauty of using marine radar is that we can get very rapid update rates due to the fast sampling of the radar. So it's great for looking at very dynamic areas where you need almost real-time intelligence on beach levels. With satellite data, we can look over much longer periods because we only get about 100 to 150 satellite images in a year, but we can look over much larger areas. And so an example of this is Morecambe Bay. Again, on the left, we have the LiDAR survey for, in this case, 2017. And on the right, this is 2018's derived map from the SAR imagery. And in this case, we've used the tide gauge at Heysham as the reference level. And it's only a single reference level. We tend to lose the quality of the fit as you go higher up into the estuary and the tide distorts. And really what we need for that is a decent tidal model. And in fact, we're working on tidal model variants of this for Accord-funded work that we're doing in Bangladesh at the moment. So in summary, this work derives pixel elevations that are relative to the tidal datum. We have two complementary approaches: marine radar for fast updates and SAR data for longer 6-month to a year measurements over much larger areas and a number of case studies. Thank you very much.
Hello, my name is Elliot Greatrix, and I'm a previous graduate from Plymouth University who took a particular fascination into remote sensing. I am now a master's student at the University of Leicester studying satellite data science, and today I'm going to talk to you about ocean colour models. And I think a good place to start is just asking, what do we see? And we see colour, and we see colour absolutely everywhere because objects hold inherent optical properties. And to give an example, if we just take the humble leaf, for example, and inside leaves are chlorophyll, and the optical properties of chlorophyll tell us that it has increased absorption in the blue, increased absorption in the red, which leaves green to be the dominant wavelength which we see. But on the other hand, what do machines see, or from a remote sensing view, satellites? Well, satellites see a value in each pixel in an image between 0 and 1, and that value is reflectance. And that is also seen throughout each individual wave band, such as red, green, and blue. And here we have an image of the southwest coast and Plymouth, and I push this image through QGIS, and we can see that on the land, reflectance in the green is higher than in the ocean. And that makes sense to us because on the land we know there's more green things such as fields and grass to lead to this increased value. But apart from statements like that, we can't really gain other meaningful data from this. So how do we do that and turn this signal into meaningful data? And we can use a model, and a model which sits quite nicely in between more simple empirical schemes and neural networks is something called a semi-analytical scheme, which uses underlying theory, which in this case is light and radiative transfer, and it uses that with the optical properties of an object and also the concentrations of that object in the environment. So an example of one of these models is displayed here, and it shows all the backscatter in an environment in a particular waveband over all the absorption in an environment in a particular waveband will give reflectance in a particular waveband, either in the green or the blue or so on. And I used this model to derive various ozone constituents in Plymouth Sound, and I did that very briefly using this method, and I essentially derived a suite of reflectances using this model, and then I compared that to in situ reflectances which were seen in satellite imagery, and if those two reflectances matched up, we could come to some conclusion about the state of the environment. So here I tested loads of constituents, but chlorophyll was one of the main ones, and it's shown here. And you can see that these results are quite interesting. There's big error bars and there's some outliers, and you can ask me about those later. But you could see as we started removing outliers, our correlation between the modeled chlorophyll and measured chlorophyll increased. But because you're removing outliers, you have to assume that your confidence in the results decreases. So that's quite an interesting, that's something that I find quite interesting from this study, how you manipulate data to kind of see what you want to see instead of what is actually there. But after all this, after some quite simple statistics and open source data, I managed to derive this map, which shows chlorophyll outflow from the River Tamar into a more homogeneous Plymouth Sound, and then into kind of the Shelf Sea. So there's a lot more going on here with how the model was made and the errors and the noise and the outliers. But that's a very brief overview. And if you have any more questions, I will be happy to take them. Thank you.
Hi there, my name's Jim Main. I'm Director at Kintech Limited. We're based in Inverness in the Highlands of Scotland. Today I'm going to talk about how we've integrated the use of USV and multi-beam technology into our data capture for a civil engineering project. Bit of background. In 2005 I took over the company, and at that stage I was only carrying out setting out. Then I moved into land surveying and laser scanning, and identified that there wasn't any capability locally to carry out data capture below the waterline. So I then started talking with Norbert, and then I identified that ideally I needed a vessel for our Norbert system to work with. So we looked at various things and we decided that a USV would be the way to go. Many reasons for that. First of all, there was demand of vessel costs and certification and training and so forth. Where we carry out our works tends to be very shallow waters. So utilising a USV improves the safety to to the individuals carrying out the survey as well. Due to the remote locations of where we go, it also meant that it was easier to launch, etc., than a manned vessel. So it sped up operations. And also it allowed us, having the small vessel, to adapt it to what our clients we needed. The journey wasn't smooth. So to start with, we had a small inflatable, then we got a glorified bait boat, for want of a better description, fitted with an Omex sender. Worked well for what we were doing, but what we needed evolved. So we purchased an off-the-shelf platform. It did for most of what we needed, but we had to adapt it as we were going along to meet our requirements. We're currently developing our own platform in-house. Can't say much about that though. There was a lot of investment made at the front end. A trailer, so the boat could be transported. It had power and an office space at the front for myself to sit in. Training, and we do have a lot of support from the manufacturers, which is very helpful, Norbit and Seafloor. A couple of examples of what we do with the boat now. So we carry out key wall inspections. Because it's a good repeatable data set, it allows us to compare different surveys over time, and you can check for bulges that appear when and where, etc. And also it can be combined with laser scan data sets as well. For this project, we carried out modelling of a sluice gate. The final project was delivered in CAD and Navisworks models. We utilised the Norbit equipped USV and laser scanners, top one laser scanners, Trimble kit as well. And it's all modelled into a single model from a combined point cloud. For this project, the client was going to flood a loch further to create a reservoir. So we utilised a combination of a UAV, a drone basically, our USV with an Norbit, and a Cessna for where it was quite steep out of that shot, obviously. For this project, we combined the USV and the UAV data again, and we also laser scanned the structure that's out with the shot. Good dense data set. All in all, it's not been a smooth journey, but it's been, the USV has allowed us to develop it as we go along. The Norbit system has been absolutely fantastic, and we'll continue to make developments with the USV all the time. Thank you.
Hi, this is Deep Learning for Noise Segmentation in 3D Point Clouds. My name is Burns Foster. I'm the R&D Project Manager at Teledyne Keras. A little bit about us. We are a marine GIS specialist software company. We've been in the business for over 40 years. So to set the stage a bit for what we're going to talk about today, we're really going to focus on point clouds. At Teledyne Keras, we're really focused on generating and managing all these large volume point cloud data sets to derive value-add products, whether that be a DTM or a set of contours, whatever might be needed by the end user. Of course, when you're collecting these data sets, no matter how good your platform is, no matter how good conditions were in the day of survey, some level of noise is going to creep in. That's going to happen. So the first thing we identified when we were looking at deep learning applications to help our end users, we focused on trying to identify and remove this noise to really speed up the end processing workflow for our users so that they can get to making their products faster and don't have to spend a lot of time trolling through the data sets and identifying and removing that noise. So this is what our AI architecture looks like for dealing with point clouds. We start with, of course, the raw point cloud georeferenced, and we actually cut it up using our variable resolution technology into smaller discrete regions. Then for each region, we run some analysis on it, and we determine the best binning size or horizontal resolution and vertical resolution for each discrete region. And the difference between variable resolution and what we're doing now is we're actually creating not a 2D grid but a 3D grid. So these are traditionally called voxel grids, and instead of binning just in the XY plane, we're also binning in the vertical plane as well. Basically what we store in each voxel is sort of an occupancy bit, we call it, whether or not there are points at that 3D position. And we can also store some additional useful statistics about those regions if it helps the AI model, and we found for different applications, of course, it does. Then each voxel grid gets passed through the GPU running on a graphics card. It does the deep learning classification part, and that comes back as a labeled voxel grid. Then we can apply that back to the source points. Probably the important thing to note about that is we're not just returning a binary yes or no for any given class, we're actually returning a confidence. So in the case of noise, we get a noise confidence value back. And what we can do is give the end user, control on what the threshold for a final classification would be. So by default, it's greater than 50%, we classify it as noise. But we can give the user control to play with that value to improve under different conditions. The other nice side benefit to this is we can actually take the deep learning model and put it up in a cloud service. One of the challenges of all this great new deep learning technology is it requires some fairly specialized high-end hardware. And that's not always practical for end users to sort of source, purchase, assemble, and maintain these high-end machines to do the AI piece. So what we can do is offer it as a cloud service so users don't have to make that capital investment. And the best part about the voxel structure is we can actually anonymize each voxel grid going into the AI. The AI doesn't care about the real-world geographic position or even the scale of the data, whether it's at 20 meters depth or 2,000 meters depth. It's looking at the shape of the data, not where it is and sort of what scale it's at. So we can anonymize that data transmission to keep your data secure. So on to some of the results. So here's a sonar survey in a river environment over a shipwreck. We've got a couple of different passes, and you can see the AI does a great job of removing both the random noise above and below the real data, as well as the systematic noise like the bubble sweep there at the top of the picture. Here's an example with terrestrial LiDAR. This is actually a Teledyne Optech Galaxy system where there was some atmospheric interference that produces a noise band above and below the data set. Unfortunately, it also cuts through part of the data set because we're in a very mountainous region. Otherwise, a sort of a simple height filter would have worked well, but in this case it becomes challenging. So the AI, this is where it really comes into its own, where it can distinguish even in a mountainous region and isolate those noise points. And then finally we have sort of a crossover, a bathymetric LiDAR. So this is an airborne LiDAR sensor, but with a green laser that can actually penetrate the water column. And in this case we're dealing with two types of noise. We have water surface reflections that need to be filtered out, as well as suspended sediment and other things in the water column. And in this case we're actually doing a multi-class classification because we're interested in where that water surface is, because that's going to impact some of our downstream calculations. So we want to identify that, as well as any suspended noise in the water column, and we're able to do that very well. On a final note, it's really important to show some of the numbers. So we divide this up into sort of several different categories. First, the noise accuracy, or how well we can classify the noise points. And as you can see, for sonar and LiDAR, we do 90%. Actually, we typically do better, but we're trying to be a little conservative in the numbers. The bathymetric LiDAR model is actually still under development. We're hitting about 70% right now, but we're very confident with some more data samples we're going to get that up into the 90% range as well. It's also important to talk about data preservation. Not only do we want to remove the noise points, but we want to make sure we don't overfilter and remove good data while we're at it. And as you can see in the numbers here, we're hitting 98-99% on that. So when we're training our deep learning models, we're putting heavy emphasis on preserving the good data at the expense of missing some of the noise points. In terms of time saving, that's also an important metric. in terms of the value that brings to the end user. This is how much better your life is going to get because you're not spending that time removing noise points. Thank you, and check us out at charismira.ai.
Hello, I'm David Vincentelli, hydrographer and director of Icebrew Sea Operation, and also president of the French Hydrographic Society. Icebrew started working on maritime autonomous surface ships, MAS, in 2015. Today, in 2020, we built, sold, and operated several of them around the world for customers ranging from national administrations such as NOAA or SHARM to private companies working in support to the energy market or the cable industry. DRIX, our first performing MAS, has been operating for 3 years now. Also, it performed very well. It also served as a development platform, and we learned a lot from our customers' requirements and hydrographic campaigns results. Capitalizing on these very good results, Icebrew is now moving forward towards a wider autonomy, meaning full ocean depth capacity, intelligent operation, and autonomous deployment and recovery of third parties, such as AUV and ROV. It means being able to adapt and develop new concepts of operation, working on transportation and integration of much bigger payload, and extend the operating range beyond the line of sight. With smaller and bigger assets lasting longer at sea, come new requirements. First one being the technical reliability of our MAS, but also a mission-based environment to support autonomy, proposing on a case-by-case basis the possibility to have LARS or not, towing capacity of third-party equipment, flexible strategy for data transfer and/or data processing, cybersecurity, vessel support. The purpose of that presentation will be to show how we, as hydrographer, develop from a platform a complete autonomous and supervised environment to go from very shallow waters to full ocean depth, with MAS that keep the same capabilities as the one shown, for example, by our DRIX, but in more various, harsher, and longer conditions. I will be happy to go through a deeper presentation of that vision in the next few months. And thank you very much for listening.
Hello everyone, my name is Brian Calder and I'm a research professor and associate director at the Centre for Coastal Ocean Mapping at the University of New Hampshire. My goal today is to give you an overview of the work that I've been conducting on volunteer bathymetric information, more commonly, if incorrectly, called crowdsourced bathymetry. Specifically, how we should treat this data for authoritative use at a hydrographic office. I think most people would agree that there is potential benefit in volunteer data, but the biggest concern is how much to trust the data and answer the question, when can we take it seriously to update a chart? A number of hydrographic offices have been developing approaches to this problem, including NOAA and the Canadian Hydrographic Service, among others. I spoke with Pete Wills from CHS Pacific Region at an IHO working group meeting when he was reporting on his use of the same volunteer data that I'm about to show you for updating the chart, and I asked him, where's the effort in this process? And his response was this: the problem is assessing the credibility with this CSB stuff, and I couldn't agree more. The core concept posed here is that of an observer reputation, which measures how much we should trust a given observer's data. This can be placed somewhere on the spectrum of credibility, with volunteer data at the lower side and fully authoritative data at the higher end, as shown here. If we can estimate an observer's position on the spectrum reliably, then we can use it to assess when to trust a particular observer and how many observations are required before we take a given action, like updating the chart. Notice that I'm not making a distinction between volunteers or professionals here. Every observer has a place on this spectrum. Without going into details, I believe I can show that we can estimate reputation by comparing volunteer data against the authoritative source where that exists, estimating all the values shown in red here from the data. The model of reputations I've chosen is based on chess rankings, which measure relative skill of players based on comparisons with others, that is, during a sequence of games. If we give the authoritative data the same reputation as an authoritative observer, then you can see that this model fits quite nicely with assessing volunteer reputation. By way of example, this is the dynamic reputation as function of time for a particular observer in the Seattle area, with the blue line showing the reputation and the red line its corresponding uncertainty over the course of 4 transitions over the area of interest here. You can see here that this is a good observer. It quickly increases its reputation to about 3000, which is considered authoritative, and then stays there over multiple observation periods with very low uncertainty. This, on the other hand, is an unreliable observer, where after initial success, the reputation drops to a mid-range value and then stays there over time. The former observer is someone that we could probably trust on the chart if even a single observation disagreed with what we currently have. This observer, however, would have to demonstrate many data with consistent results to be taken seriously for a chart update. The reason for this behaviour, incidentally, is that this observer is very noisy. Although it often matches the known depths well, as you can see in the top panel there in blue, as you can see there in red, the difference frequently departs from the reference, albeit for short periods, way more than the uncertainty, which is the bottom plot would suggest. The reputation assessment recognises this and penalises the observer accordingly. Reputation is not forever, however. Here, the first observer, for some unknown reason, starts to misreport the depth, and then disappears from the record for about 4 months. When it returns, the reputation quickly returns to optimal again. I don't know why this happened, to be honest, but it's tempting to believe that this was a temporary adjustment to the ship before an extended cruising period. Again, the reputation system sees that as a function of time, compensates, and then recovers as the data starts to improve again. There are, of course, many details on how to do the estimation and its implications. The summary, however, is that I believe that we can assess reputation for volunteer observers using only their observation data, and that we can track changes over time, and that authoritative observers can also be assessed in the same way. Now, the implications of this model also go a little bit deeper, since you can also think of the reputation of the data being inherited from the observer and then existing on its own over time, which leads us into interesting conclusions on chart quality assessment and resurvey priorities, among other things, which I'll be very happy to share with you when we're able to meet again in person. For now, however, I'll leave you with my contact details here, and note that for now email is probably the best way to get in touch, since we expect to be working from home for the near future. I'd also like to gratefully acknowledge the NOAA grant noted here, which supported this work. I look forward to seeing everybody at the conference eventually. In the meantime, thank you for listening.
Welcome, and thank you for the opportunity to discuss compact USVs and extending their reach. We'll take a look at some of the applications, and in particular a USV that's fitted with a EdgeTech 2205 sonar, the engineering challenges, a case study, and some future enhancements. So here's some facts and figures about the sonar system. And considering the engineering challenges we faced, in regards to electronics, we were able to reduce the power requirement, which is of direct benefit to the USV, because of course that improves the battery endurance for the smaller vehicles. The second improvement was to reduce the heat output, and that means there's no additional need for heat dissipation systems, which is of course a direct benefit. Concerning the arrays, previously they were more brick shaped, and then we fitted a fairing around them to make them more hydrodynamic. And then the new arrays are already of a hydrodynamic nature, again improving the endurance of the vehicle. Taking a look at some of the results, the first case study, habitat mapping. By way of example, one line of side scan and bathymetry coverage. Some of the lines from the bathymetry merged together, and then the low frequency mosaic, and probably an area of dense seagrass compared to an area of sparse seagrass. And by way of indication, what different densities of seagrass might look like with one particular frequency of side scan. So looking at the side scan results in a little more detail, the area of probable dense seagrass presents itself like this. And conversely, the area of sparse seagrass presents itself like this. And it's worth mentioning motion-tolerant side scan, a feature of EdgeTech sonars. As well as the standard low frequency and the standard high frequency, we offer a third output, which is the motion-tolerant, where we do some slightly different signal processing. You can see here this banding is typical when the vehicle experiences pitch or yaw because of the sea conditions. Less noticeable in the motion tolerant, and that makes for easier interpretation during post-processing. And not uncommon in acoustic mapping projects to have marine mammals not too far away from the survey vehicle, and here you can see nicely captured in the sonar records dolphins or porpoises, a small school of them, coming to say hello. And so what's coming? What's new? What's the latest news? Firstly, sub-bottom profiler. So here you can see fitted to the vehicle the transmit unit, and then this panel is the receive unit for our sub-bottom profiler. And then secondly, a new frequency pairing, not 540, 1600 that we've been talking about, but the latest sonar will be 800 and 1600 kilohertz as the frequency pairing. And so briefly in summary, the compact USVs that we've seen as part of this presentation really are an ideal solution for companies looking to get reliable operation and top quality data results. And always good to take into consideration a sort of plug and play capability, allowing the payload to be exchanged so that the vehicle is suited to a number of different site-specific requirements depending on the application. And then in closing, thank you very much for the opportunity again, and feel free to contact EdgeTech for further information on the sonar systems that we offer. And thanks again to Sea Robotics for their cooperation in participating in this little presentation. Thank you.
Hello, I'm David Parker, Chief Executive of the Hydrographic Society UK. I hope that you've enjoyed watching our short Prelude presentations from a range of speakers selected from the full programme of our remote hydrography conference. We are sorry that we were once again forced to delay the in-person event due to COVID-19, but I'm sure you will understand. We hope today that we've given you a taster for the main event, to be held hopefully in the spring of next year at the National Oceanography Centre in Southampton. Today we've had a brief insight into the range of developments around the remote hydrography theme, ranging from unmanned survey vessels, AI in data processing, satellite observation and crowdsourced data. All of these share a common theme, a further shift towards removing the hydrographer from the immediate front line, whether it be on a survey vessel or undertaking the heavy lifting in the data cleaning stage. However, I feel the evidence is also clear that hydrographers are no less important to develop, plan, supervise and assess these processes than at any point in the past. In fact, I would argue individuals within our profession actually need to further expand their education and skill sets to make a success of these new opportunities and technologies, while ensuring key standards are attained. Promoting and protecting our profession, as well as providing opportunities for development and education, is the core purpose of the Hydrographic Society UK, as well as our sister organisations overseas. As well as staging events, THS UK and the Federation of Hydrographic Societies will soon be launching a hydrographic professional accreditation scheme, which will certify individuals to one of 4 levels within the hydrographic profession. More to come on this soon. So, if you are watching this and not already an individual or corporate member of your National Hydrographic Society, then I encourage you to join your professional community and participate. Remember, today is just a prelude, designed in part to compensate you for your patience while our conference is yet again delayed by COVID, but also to whet your appetite for the main event next year. I hope we've left you with some questions, which can be brought to our speakers in person soon. So finally, I would like to end with some thanks. Thanks to our speakers, who all contributed their videos at fairly short notice. We look forward to seeing them with their full presentations next year. Thanks to Rear Admiral Sparks, and again we look forward to hearing his full keynote. Thanks to NOC, who as our host venue have live streamed this event today and compiled the content. Finally, thanks to the THS UK Remote Hydrography Working Group for their continued hard work and adaptability. So that's it for now. We look forward to seeing you all next year.